The first topic that I want to talk about is bias mitigation during the model training stage or in processing. And keep in mind here we're following the typical life cycle of a machine learning model. So we had a look at the data preparation and exploration, at algorithm selection, and then a final mitigation step that we can take when it comes to transforming the data or potentially deleting any features that we don't want to include in the model training. Now we're going to talk about what we can do during the actual training process of the model itself. The first topic here that I want to touch on is constraining the training process. And before we can talk about what it means to constrain the model training, we need to take a quick detour and have a look at a very important topic in machine learning called regularization. So what does regularization in machine learning stand for? It means that we want to tune the model complexity by adding a penalty term for complexity to the cost function. So we've already looked at what the cost function is all about. It's C of W, cost function of the weights or parameters. And then we have this penalty term plus alpha times penalty of W. So the alpha, that's going to be a scaling factor of how heavily we want to penalize, and then the penalty function itself can take different shapes. We have two examples here of penalty function. On the left-hand side, you have the L2 regularization, also called ridge regularization. And on the right-hand side, you have the L1 or lasso regularization, where it's the sum of all the absolute values of the W's, the weights, or the parameters. And what we can see here is that using these penalty terms, we can either shrink some of the weights all the way to zero or make them close to zero, and thereby we will eliminate certain factors from our equation. A very important note here is that we do need to scale our features first for this to work. So this is again coming back to some of the data preparation and best practice in machine learning, but we always want to make sure that we scale our data. There are different use cases for this. One that we're seeing right now is regularization, and then the other example that I gave earlier is that a lot of the models that you will use actually depend on distance measures, and those also need to be using scaled data. So why do we need regularization in machine learning? Well, here's the concept of overfitting and underfitting that comes in here. And overfitting refers to a model memorizing or imitating the training data too much. And an overfit model will fail to generalize well on new and unseen data. So basically what that means in a nutshell is that your model will work really well on the training data. And keep in mind here, you've already, or you should have performed a train, test and validation split. And the model will work really well and achieve high performance on the training data. But then when you test it on the test data, the performance will suddenly go down. So that means you've overfit on your training data. You're just imitating what you see in the training data, but you don't generalize. So that means the model is too complex. It might be picking up on noise instead of the true underlying patterns in the training data. And as I just mentioned, the model will perform well on training, but poorly on validation and obviously also on the test data. And to avoid this overfitting occurring, well, this is where regularization comes in. On the left-hand side, you also have a visualization of what it could look like for a classifier to be overfit. So you see here that the decision boundary is going very granular and basically carving out some of the positive instances, but that decision boundary will not be upheld when it comes to test or validation data. So what happens then when we actually include regularization in our modeling approach? Well, it leads to appropriate fitting. So that means the model now actually captures the general relationship between the input data, the features, the X, and the output, the target Y, which could be classes 1 and 2, or approved and denied as in our example here. So an appropriate fit means that the model is not too simple, it's not too complex, it's well balanced, and we actually pick up the underlying relationship rather than the noise in the training data. So the model will then perform well on the training, the validation, and the test data. Do keep in mind here that we have a bias and variance trade-off that applies. And if you want to learn more about bias and variance trade-off, then have a look at the MLU Explain article that explains this in an interactive visualization. So you might be wondering now, what does regularization have to do with fairness? Remember, the topic here is the intervention that we can take during the model training stage. And what I'm going to show you now is how we can actually take the constraints and modify them slightly to make them work as a fairness penalty or constrained training of the model. So the idea now is, rather than constraining for model complexity, we're going to constrain for model complexity and also impose a fairness constraint. So there's going to be a trade-off between the model performance and the fairness constraint that we want to enforce. That means the problem that we want to solve now is we want to minimize the cost function, which is a function of the model parameters, plus a regularization term where we have omega as a convex regularization term and beta as a trade-off parameter, subject to a fairness constraint, such as the difference in disparate impact needs to be below equal to an epsilon threshold. What you're going to find is that this is actually quite hard to implement in practice because this constraint is non-convex. So what we need to do is we need to reformulate the problem expression and turn it into a convex formulation. So instead we want to consider minimizing the loss, plus we now have a lambda term and R dtp, which is a convex approximation of the fairness constraint, and again our final regularization term. Another way to modify the training process of a model would be through so-called adversarial learning. So we're not going to go too much in depth onto this particular topic, but I want to give you a high-level overview of what it means to perform adversarial learning and how we could achieve fair adversarial learning. Adversarial learning in general is a model competing versus another model. So we have a target model, which would be synonymous to the models that we've built so far, and that model aims to predict y hat. And we're going to use a subscript t for denoting the target model and then the target predictions. And as with every machine learning model, the idea here is that we want to have the best possible performance. Now we have a second model, the adversary model, M subscript V, and that now aims to predict the sensitive attribute using the output from the target model. And the idea here now is that if the target model does not rely heavily on the sensitive attribute, well then the adversary model will have a very hard time re-engineering what the sensitive attribute is. So if indeed MT is fair, then y hat t is not going to be useful for the adversary to predict the sensitive attribute. So in a nutshell, we want the original model to do as well as possible, while also minimizing the success of the adversary. Let's look at all of this again in pictures. What we have here in the top left corner is a tabular dataset. One of the features, X subscript A, is denoting a sensitive attribute. On the far right, we have Y subscript T, and that's the target that we want to learn to predict. So the model M subscript T is now taking the inputs, all of the features, in combination with the target to create predictions Y hat T. And the idea is that if MT is a reasonably good model, well then the predictions or the performance with Y hat T should be reasonably good. What happens next is the adversarial M subscript V is now going to consume these outputs, or sometimes outputs in combination with some of the data from the original dataset, and it's trying to re-engineer the sensitive attribute X subscript A. So now this is going to be a prediction, and that's why we denote it as X hat A. And as I mentioned just a moment ago, the idea is to maximize the success of MT, so the original model, while minimizing the success of MV. similar to limitations that we had for pre-processing methods, we need to talk about limitations for modifying the training process itself. And we already called this out when we actually talked about the different techniques that we can deploy, but here again a summary. Problem number one is that applying constraints can actually make it hard to find a solution. So we might actually not converge to a solution, and then we need to relax the problem formulation. And the relaxed constraints, and this is the second bullet point here, are often a poor approximation of the actual constraint that we care about. So that means even if we maximize, even if we achieve our objective, the model might remain unfair. Secondly, the types of algorithms are actually very restricted. So this constrained learning, or also the adversarial learning, will not work for all algorithm types. So we actually have to restrict from the families of algorithms that we can select from to make these techniques work. Obviously, these are only a couple of examples of limitations, so I would encourage you to read the paper by Lohas et al. To get more details on these issues.